Hey everyone. So in chemistry, knowing exactly when a reaction is done is, well, it's everything. But what do you do when you can't actually see the finish line? Today, we're going to look at a super clever technique that lets chemists see the unseen, using electricity to find a reaction's end with, honestly, incredible precision. All right, let's just dive right in with a question. Imagine you're mixing two clear liquids, and you're waiting for that one moment it changes color to tell you the experiment is done. Sounds simple, right? But what if your solution is already super dark, like black coffee? Or maybe it's completely cloudy. How in the world are you supposed to see a subtle color shift in that? That's not a trick question. It's a real everyday headache for chemists. And yeah, that gets us to this fundamental challenge, knowing precisely when a reaction has hit its endpoint. For a long, long time, chemists just relied on their eyes and these little things called visual indicators, chemicals that, you guessed it, change color. But our eyes can be tricky, and in a lot of situations, they're just completely useless. So this brings us to two totally different ways of thinking about it. On one hand, you have the classic visual titration. It's simple, it's fast, but it's also subjective. You know, what you call pink, I might call light pink. And like we just said, it's a total non-starter for colored solutions. But then there's potentiometric titration. This method is precise, it's objective, and it completely gets around the need to see anything at all. So what's the big idea here? It's actually pretty simple and kind of brilliant. Instead of looking for a color change, we're going to listen for an electrical one. We're literally going to measure the solution's voltage as the reaction happens. And that right there is what potentiometric titration is all about. It's a method where we find that endpoint by spotting a sudden, dramatic change in the electric potential. You can just think of it as voltage. The key thing to remember, we don't need any visual indicator. We're basically using a voltmeter as our eyes. Okay, so to pull this off, we need two key players, the electrodes. You can basically picture them as two special metal probes that we just dip right into our solution, and they're what's going to measure that electrical potential for us. Now, these two electrodes have very different jobs. It helps to think of them as a team of two totally different characters. First, you've got the reference electrode. This one is the stoic, steady one. It gives us a constant, stable electrical baseline that never changes. And then you've got the indicator electrode. This is our super sensitive detector. Its potential changes because the charged particles in the solution, the ions, are constantly interacting with its surface. As their numbers change, so does the electrical pressure it feels. And that's what we're measuring. And this is really the key. Our instrument isn't just measuring one or the other. It's constantly, second by second, measuring the difference in voltage between our stable reference points and our hypersensitive detector. And that difference, that's where all the magic happens. Okay, so we're getting all this voltage data. What do we do with it? How do we make sense of it? Well, this is where it all comes together to give us a signal that is just impossible to miss. What we do is we make a simple graph. On the bottom axis, the horizontal one, we keep track of how much chemical we're slowly adding to the mix. And on the vertical axis, we plot that real-time voltage difference our electrodes are measuring. And you know what's cool? As you start plotting these points, a very specific, very recognizable shape starts to form. Just like our source material says, you can very clearly see we will get a sigmoid shape graph. Now, sigmoid is just a fancy word for something that looks kind of like the letter S. So you're looking at this S-curve, and you might be thinking, okay, but where is the finish line? I mean, the voltage is changing the whole time, right? What's the specific signal that we're supposed to be looking for? And this is what makes the technique so powerful. The endpoint isn't just some random point on the curve. It's that sudden, incredibly steep jump right in the middle of the S. So why does it spike like that? Well, it's because at that exact moment, the chemical we started with has just run out. The very next drop of stuff we add has nothing left to react with, and that causes a massive, sudden shift in the solution's chemistry. That almost vertical line is our signal. It's a clear, objective, impossible-to-miss sign that the reaction is done. So, let's wrap this up. Why has this method become so incredibly important, especially in fields like making medicines, where getting things exactly right isn't just important, it's absolutely non-negotiable? Well, first off, you don't need a visual indicator. That makes it perfect for all those dark or cloudy solutions we were talking about. It also gives you way more reliable, objective data, totally avoiding what chemists call indicator error. Plus, because it's all based on an electronic measurement, the whole process can be easily automated, which makes labs incredibly efficient. And get this, it's not some one-trick pony. This technique is a real workhorse in the lab. It's useful pretty much across the board, whether you're measuring acidity, tracking electrons in a redox reaction, or even watching solids form. It's a truly versatile tool. So I'll leave you with this idea. Potentiometric titration is way more than just a clever lab technique. It's a great reminder that sometimes the most critical moments, the most important changes, are the ones we can't actually see with our own eyes. We just have to learn to measure them in other ways. Thanks for diving into this with me.